Hey guys, how's it going? Here is a quick video to help you through this week's lab. In essence, what we're going to do in this experiment is really 5 separate things. We're going to generate some experimental data, plot the data, determine when the chemical system reaches equilibrium, so it's a third thing, try to calculate out an equilibrium constant for your particular chemical system, and then repeat the experiment again, but at a different temperature. 5 different things that we're going to do. Now, some general advice to consider while you're doing this experiment. Do everything in your laboratory notebook. It's okay if you make mistakes in there. Remember, single line through mistakes, and then just continue writing afterwards. It's totally okay to mess up in your lab notebook as long as it's clear that you messed up. No whiteout, don't scribble anything. Additionally, before I forget, make sure that you guys don't ever use pencil in your laboratory notebooks. You always want to use blue or black ink. Remember, this is supposed to be a permanent record. So when you're using your laboratory notebook, only use blue and black ink. The other piece of advice I'll give you is collaborate. Please, please, please collaborate. I'm putting you folks in teams specifically for a reason, and that is so that you can bounce ideas off of each other. To show you how this experiment's going to work, we're going to use this kind of as a case study. It says chemicals A and B are known to react until reaching equilibrium. A reaction vessel initially contains 3.2 molar A and 3.2 molar B. If at 25 degrees centigrade, Kf equals 0.10 per second and Kr equals 0.25 per second, what is the equilibrium constant, or KEQ, for this process? This is very similar to the type of experiment that you're going to do. You will not have these same values in this experiment. You will have these similar Kf and Kr values to use in your experiment. All right, the first thing to consider here is that this process is in fact in equilibrium. So we have chemical A is in essence in equilibrium with chemical B. So there's competing processes that are going on. A is being converted into B, but at the same time, B is being converted back into A. The rate for the forward process is simply defined as Kf, so it's going to be this value, multiplied by the concentration of A. If we want to know the reverse reaction, that is going from B to A, all we have to do is take Kr, 0.25, and then multiply it by whatever concentration that we're talking about. Now, one thing to point out here is that during this experiment, your concentrations are going to change. So 3.2 is going to change, and 3.2 for B is also going to change. However, the values for Kf and Kr are going to be constants. They're not going to change at all. All right, so let's talk about how you go about generating your data. All right, so if you open up your packet, you're going to see a data table that looks for something like this. All right, so a couple things to point out. First and foremost, this delta A, or delta concentration of A divided by delta T, is really just rate. That's what that means. The units are going to be in molar per second. So you'll do this for A, and then you'll do this for B. The rates are going to change over time, and so will the concentrations of A and B. And those are what I've noted here in red. These are concentration values for A and B. All right, so with that in mind, let's go back to the problem for a second. We need 3.2 molar A and 3.2 molar B. Those are our initial concentrations. So we're going to plug that data in, time equals 0. So we'll put a 3.2 here and a 3.2 there. All right, so now how do we calculate out the change in the concentration of A over the change in time, or the rate of A and then the rate of B? How do we do that? Well, if you remember, the rate for the forward process was just Kf multiplied by the concentration of A. So in this case, we look at the value for Kf. We saw that the value is 0.1 per second. So we'll go ahead and put that number in right here. And then we're going to multiply by the concentration of A right now, 3.2. So we're going to put this number in. So in essence, we'll multiply these two together. And when we multiply them together, we find out that the forward rate is 0.32 molar per second. Now that we have that value, we're going to go ahead and plug that into our data table. The rate of the reverse reaction is just going to be the rate constant times the concentration of B. So when we do this, we put our 0.25 per second in here, and then we're going to multiply that by 3.2 molar. So we'll multiply these two across, and then we find out that the reverse rate here is 0.80 molar per second. So I'll take that number and we'll put that into our data table as well. Now we have an idea as to where all this data is going so far. So now let's take a look at what happens at time equals 1 second. So for us to calculate out the concentration of A at time equals t, in this case 1 second, what we're going to do here is we're going to consider the fact that we've got to look back at the initial concentration at the time interval before that. So before it was 3.2, but remember 0.32 molars of that has actually reacted over the first second. So to symbolize that mathematically, what we're going to do is we're going to take our 3.2, which is here, and then we're going to subtract 0.32 molar from that. But then we also have to keep in mind that B is working backwards to produce more A. So we have to consider the fact that while A is reacting at a rate of 0.32 molar per second, B is producing more A at a rate of 0.80 molar per second. So we add that in. This is where this 0.80 molar comes from. When we do all of our math out, we find out that the new concentration for A at 1 second is 3.68 molar. So now we're going to take that value and we're going to plug that in. Now we're going to calculate our concentration for B at 1 second. So same basic principle. The concentration of B at any given time interval is just going to be the concentration of B at the previous time interval. We're going to subtract the rate at time equals 0, and then we're going to add the rate for the formation at time equals 0 as well too. So in essence, what we're going to do here is we're going to take our 3.2, we're going to subtract 0.8, and then we're going to go ahead and add 0.32 to that. And when we do that, we find out that our new concentration for B at time equals 1 second is 2.72. So we're going to take this value and we're going to go ahead and plug him into the equation. We can now calculate out the new rate of formation. The rate for the forward process, that is going from A to B, is just simply going to be Kf times the concentration of A for that given time interval. So we're going to use our Kf, 0.1 per second, and we're going to multiply that by 3.68, and that will give us our new rate. You'll notice how the rate is actually changing between the time intervals. What would the next value be? Would it be 0.72, 0.88, 0.68, or 0.41? Pause the video and see if you can calculate it out real quick. All right, if you've calculated this out, you'll hopefully find out that the answer is 0.68. Plug that number in right there. Let's see what the concentration of A is at time equals 2 seconds. Is the answer going to be 2.69, 3.71, 3.50, or 3.99? Pause the video for a moment and see if you can calculate out the correct answer. You'll find out that the new concentration should be about 3.99. Take a look at the equations that we've seen in the previous slides. A at time equals t is just simply going to be the concentration of A at the previous time interval. So that's going to be 3.68 subtracted from the change in concentration of A divided by the change in time at the previous time interval. Then we're going to go ahead and add delta B divided by delta t at the previous time interval. So in essence, what we're doing here is we're taking, look at the previous time interval to try to calculate this out. So this is 3.68 molar subtracted from 0.37, and then we'll add 0.68. And so when we add all of these together, we do all this arithmetic, we're going to find out that the answer is 3.99. So in essence, that's how you go about calculating out this experimental data or generating your experimental data. When you're doing your calculations, you can stretch this thing out to 10 decimal places if you really want to. I think that's an overkill for this experiment. All you really need to do is calculate out to 2 decimal places, and that will give you good enough data. Not 2 sig figs, 2 decimal places. The other thing to consider, students will sometimes ask, how long should I calculate this for, or how many rows should I calculate for? My advice is anywhere from 15 to 20 seconds is usually good enough to determine when the equilibrium actually forms. So what that means is you'll do basically 15 to 20 rows worth of data until eventually you have a complete data set. And again, just to remind you folks, make sure that this is all recorded in your laboratory notebook. All right, so one thing that students will sometimes ask is, how do you tell if the data is actually reasonable? So everything's basically been calculated out to about 12 seconds here. How do we determine if this data table looks good or it looks bad? The first way to tell is by adding up the concentrations of A and B. Okay, so here I'm going to take 3.20, I'm going to add it to 3.20 as I've done over here to the right hand side, and we see it adds up to 6.40. Time equals 0. Pick any other time interval that you want. Pick any other time measurement that you want. So I picked 7 seconds. I did 4.50 added to 1.90. Adds up to 6.40. Same deal here. Time equals 11 seconds. 4.56 plus 1.84, that works out to 6.40. So my point here is that if you've done your calculations correctly, the concentration should add to a consistent value. In the example that I'm working, they worked out to 6.40 at all times. Here's some other evidence. If I take a look at the concentration of A over time, there's a pretty drastic change in concentration for the first few seconds, and then it gets kind of boring afterwards. So between time equals 0 and time equals 1, we see that the interval changes, well, almost about 0.5 seconds here. And then the interval gets smaller and smaller and smaller. And then basically towards about 11 and 12 seconds, it basically gets non-existent at that point here. So that, again, another piece of evidence to show us this. If we've done our calculations correctly, we should see pretty big concentration interval differences in the first few seconds of the experiment. And then towards the end, we should see very small changes in concentration. So now how are we going to plot our data? So we have our complete data set that kind of looks sort of something like this. First of all, we want to take a look at the time intervals that are here. This is, for this column of data, we see that it's time reported in seconds. It goes from 0 all the way to 12. We're going to classify this as the independent variable. It is the thing that you, the scientist, are controlling. That's very common in these types of kinetic plots to control time. This is going to go on the x-axis. Okay, another piece of data that you're going to want to pay attention to is the concentration of A. We're going to classify this as the dependent variable. It's something that the experiment depends upon. It is, in essence, the experimental measurement that we're after today. Since it's the dependent variable, we're going to put it on the x-axis. The other dependent variable we're going to put on our data is going to be the concentration of B. It's another experimental measurement, so it also belongs on the y-axis as well too. Okay, so we always put the dependent variable on the y-axis. We always put the independent variable on the x-axis. And you'll always remember too to put a title on top of the graph, and that is so that the reader understands exactly what they're looking for. Let's just take a quick detour here. If you want a quick bonus point, send me a quick email, jcar@cac.edu, and just send me some sort of a message, but in the subject line write everybody's favorite phrase, roll tide roll, and we'll get you a bonus point. But shh, don't tell anybody. So what is our data plot going to look like when we apply all the appropriate labels to it? Our title will go across the top here. I've picked a pretty descriptive title for this. So this is a kinetic plot. We're looking at the change in concentration as a function of time. That's generally classified as a kinetic plot. For the equilibrium of chemicals A and B at 25 degrees centigrade. I'm going to specify the temperature here because we're going to change the temperature in another experiment. So we'll put some sort of a label on the y-axis here. These are the concentration of A and B. And then notice how I'm also putting my units, which are molar, in parentheses. We want to specify which unit we're referring to. On the x-axis, we'll go ahead and write time because it's not obvious to the reader. And in this case, we'll define time using the unit seconds, which is just a lowercase s. If you've titled your graph paper correctly, you should have everything ready to go to start plotting this data. We're going to stop the video right here. The rest of this is pretty straightforward. If you follow the instructions, it should be pretty obvious how to answer the rest of the questions here. It should be pretty obvious how to address the rest of these items that are on this slide. Just one last thing I'll point out to some advice for when you're plotting your data. Make sure that you can plot it by hand if you want to. If you're proficient using graphing software like Microsoft Excel or Google Sheets, you can use those if you want to. If you do use them, make sure that you print everything and then paste it into your laboratory notebook. Make it a permanent part of your laboratory notebook. I recommend using different colors for A and B. You're going to have to plot both on each graph that you do. So as you're doing that, pick 2 different colors. Also, don't forget your units when you're doing your calculations and you're putting your data together. Units are incredibly important. All right, guys, good luck with your experiments. If you have any questions, comments, or concerns, you can email me, jcar@cacc.edu. Roll Tide, roll.